Welcome to our cosmic exploration of a truly earthly phenomenon. Ice ages. These colossal periods of glaciation have left an indelible mark on our planet, shaping its landscapes, influencing its ecosystems, and even affecting the course of human history. But what exactly triggers these icy epochs? And how do they end? Today, we embark on a journey to unravel these mysteries. These periods of vast glacial expansion, where ice sheets stretched across continents, might seem like events from a distant past, but their echoes resonate even today. The remnants of these ice ages can be seen in the form of majestic glaciers, deep fjords, and the very soil beneath our feet. The story of ice ages is not just a tale of cold and ice, it's a narrative of survival, adaptation, and transformation. We're about to embark on a journey through the intricate workings of our planet to understand the forces that plunge Earth into these icy epochs. The Earth's climate system is a complex web of interactions between the atmosphere, oceans, land, and ice. To truly grasp the phenomenon of ice ages, we must delve into the heart of this system and explore the myriad factors that influence it. You see, the Earth's climate is not a static, unchanging system. It is a dynamic entity, constantly evolving and responding to various internal and external stimuli. From the changing seasons to the shifting climate zones, the Earth's climate is in a perpetual state of flux. This dynamism is driven by a multitude of factors, each playing a crucial role in shaping the climate. It's a dynamic interplay of numerous factors, a cosmic dance of celestial mechanics, geological upheavals, and even biological processes. The Earth's orbit around the Sun, its axial tilt, and its precession all contribute to the cyclical nature of ice ages. Volcanic eruptions can inject vast amounts of aerosols into the atmosphere, cooling the planet. Meanwhile, the evolution of life on Earth, from the proliferation of photosynthetic organisms to the rise of mammals, has also played a significant role in modulating the climate. Over millions of years, this intricate ballet has produced periods of intense cold, the ice ages, that have profoundly shaped the face of our planet. These glacial periods have carved out valleys, formed mountain ranges, and created vast plains. The evidence of these ancient ice ages is etched into the very fabric of our planet, from the striations on rocks to the layers of sediment in the ocean. We'll delve into the top 10 reasons behind these dramatic climate shifts, unraveling the mysteries of orbital variations, tectonic plate movements, and the ebb and flow of greenhouse gases. The Milankovitch cycles, which describe the variations in Earth's orbit and tilt, are a key driver of ice ages. Tectonic activity can alter the configuration of continents and ocean currents, influencing the global climate. Greenhouse gases, such as carbon dioxide and methane, trap heat in the atmosphere and can either amplify or mitigate the effects of these other factors. From the depths of our oceans to the outermost reaches of our solar system, we'll examine the interconnectedness of these factors and their impact on Earth's climate. Ocean currents play a crucial role in redistributing heat around the planet, and changes in these currents can trigger or end ice ages. The Sun, our primary source of energy, also goes through cycles of activity that can influence the climate. By studying these various components, we can begin to piece together the puzzle of ice ages. Get ready to explore the science behind these glacial giants, because understanding the causes of past ice ages is not just an academic exercise, it's a window into the future. Ice cores extracted from the depths of glaciers provide a record of past climates, revealing the composition of the atmosphere and the temperature of the planet over hundreds of thousands of years. By analyzing these ice cores, scientists can identify the triggers and feedback mechanisms that lead to ice ages. It's crucial for comprehending the present and future of our planet's climate. The lessons learned from past ice ages can help us understand the current trends in global warming and predict future climate changes. By recognizing the natural cycles and human influences on the climate, we can develop strategies to mitigate the impacts of climate change and protect our planet for future generations. Let's begin our journey into the fascinating world of ice ages. As we delve deeper into this topic, we'll uncover the intricate connections between the Earth's climate system and the forces that drive it. From the microscopic organisms in the ocean to the vast ice sheets that cover continents, every element plays a part in this grand narrative. So buckle up and get ready for an adventure through time and space as we unravel the mysteries of ice ages and discover the secrets of our planet's past, present, and future. Our planet's journey around the Sun is not a simple, unchanging circle. Instead, it's an elliptical path that varies over time, influenced by a myriad of cosmic forces. This elliptical orbit means that the distance between Earth and the Sun changes throughout the year, affecting the amount of solar energy our planet receives. It's more of an intricate waltz, influenced by the gravitational pull of the Sun, our Moon, and even the giant planets in our solar system. These gravitational interactions create a complex dance that subtly shifts Earth's position and orientation in space. Now imagine these gravitational nudges playing out over thousands of years, subtly altering Earth's orbit and the tilt of its axis. These changes are part of what we call Milankovitch cycles, named after the Serbian scientist Milutin Milankovic, who first theorized their impact on Earth's climate. These subtle variations, known as Milankovitch cycles, might seem insignificant at first glance. However, they have profound effects on our planet's climate over long periods. The cycles include changes in Earth's eccentricity, axial tilt, and precession, each contributing to the way solar radiation is distributed across the planet. But over vast stretches of time, they cause significant shifts in the amount and distribution of solar radiation reaching the Earth. For instance, when Earth's orbit is more elliptical, the difference in solar energy received between the closest and farthest points in its orbit becomes more pronounced, leading to more extreme seasonal variations. And that, my friends, is where the plot thickens. These changes in solar radiation can trigger a series of climatic shifts, setting the stage for dramatic transformations in Earth's environment. Over millennia, these shifts can lead to the onset of ice ages, periods when vast ice sheets cover significant portions of the planet.
Imagine Earth receiving slightly less solar energy during its yearly orbit. This reduction in solar energy might seem minor, but it can have a cascading effect on the planet's climate. Cooler summers mean that the snow and ice that accumulate during winter don't completely melt away. Summers become cooler, winters harsher, and snow in high latitudes doesn't melt away as easily. Over time, this leads to the buildup of ice sheets and glaciers, particularly in regions like North America and Eurasia. This sets the stage for a fascinating feedback loop. As snow and ice accumulate, they create a reflective surface that bounces more sunlight back into space. This reflection reduces the amount of solar energy absorbed by the Earth's surface, leading to further cooling. As snow and ice accumulate, they reflect more sunlight back into space, further reducing Earth's temperature. This process, known as the albedo effect, amplifies the initial cooling triggered by orbital variations, and voila, we're on the road to an ice age. The albedo effect is a powerful force in Earth's climate system. When large areas of the planet are covered in snow and ice, the increased reflectivity can lead to a significant drop in global temperatures. This cooling effect can perpetuate the growth of ice sheets, creating a self-reinforcing cycle that drives the planet deeper into an ice age. Scientists study ice cores and other geological records to understand past ice ages and the factors that triggered them. These records provide valuable insights into how Earth's climate has changed over millions of years and help us predict future climatic shifts. Ice cores, in particular, are like time capsules, preserving layers of ice that have accumulated over thousands of years. By analyzing the trapped air bubbles and other particles within these layers, scientists can reconstruct past atmospheric conditions and gain a better understanding of the processes that drive ice ages. Modern climate models incorporate data from these historical records to simulate future climate scenarios. By understanding the natural cycles that have influenced Earth's climate in the past, we can better predict how human activities might impact the planet's future climate. Human activities, such as the burning of fossil fuels and deforestation, are adding new variables to the equation. These activities increase the concentration of greenhouse gases in the atmosphere, which can amplify the natural processes that drive climate change. Greenhouse gases trap heat in the atmosphere, leading to a warming effect that counteracts the cooling trends associated with Milankovitch cycles. This interplay between natural and human-induced factors makes predicting future climate changes more complex. The melting of glaciers and ice sheets, rising sea levels, and more frequent extreme weather events are all indicators of the profound impact that human activities are having on Earth's climate. Understanding the natural cycles that have shaped our planet's climate in the past is crucial for addressing the challenges we face today. Scientists and policymakers are working together to develop solutions that mitigate the impact of human activities on the climate. Renewable energy sources, sustainable practices, and international agreements are all part of the effort to reduce greenhouse gas emissions and protect our planet for future generations. As we look at Earth from space, we are reminded of the interconnectedness of our planet's systems. The delicate balance of forces that drive climate change, both natural and human-induced, highlights the importance of global cooperation in addressing the challenges we face. By understanding the past and taking action in the present, we can set the stage for a more resilient and sustainable future. The story of ice ages and climate change is a reminder of the power of nature and the responsibility we have to protect our planet. Thank you for joining us on this journey through time and space. Together we can make a difference and ensure a brighter future for generations to come.
Beneath our feet, hidden from our everyday view, lies a dynamic layer of our planet constantly on the move. The Earth's tectonic plates. These plates are not just static pieces of rock, they are part of a complex and ever-changing system that has been shaping our planet for billions of years. The movement of these plates is driven by forces deep within the Earth, where heat from the planet's core causes the mantle to flow, creating currents that push and pull the plates in different directions. This process, known as plate tectonics, is responsible for the creation of many of the Earth's most dramatic features, from towering mountain ranges to deep ocean trenches. These massive slabs of rock are constantly shifting, colliding and grinding against each other, shaping the very continents we live on. When tectonic plates collide, they can create powerful earthquakes and volcanic eruptions, which can have devastating effects on the environment and human populations. But these collisions also play a crucial role in the long-term evolution of the Earth's surface, creating new landforms and recycling old ones. For example, the Himalayas, the highest mountain range in the world, were formed by the collision of the Indian and Eurasian plates, a process that began around 50 million years ago and continues to this day.
Now you might wonder, what does the movement of continents have to do with ice ages? The answer lies in the way that the movement of tectonic plates can influence the Earth's climate over long periods of time. As continents drift across the globe, they can change the distribution of land and sea, which in turn affects the flow of ocean currents and the circulation of the atmosphere. These changes can alter the amount of solar energy that different parts of the Earth receive, leading to shifts in temperature and precipitation patterns. Over millions of years, these shifts can add up to significant changes in the Earth's climate, including the onset and end of ice ages. Well, hold on to your hats, because we're about to uncover a fascinating connection. The movement of tectonic plates can also influence the Earth's climate in more subtle ways. For example, the formation of mountain ranges can affect wind patterns and precipitation levels, creating new climates in different regions. The uplift of the Himalayas, for example, has been linked to the development of the monsoon system in South Asia, which brings heavy rains to the region each summer. Similarly, the opening and closing of ocean gateways, such as the Isthmus of Panama, can alter the flow of ocean currents and the distribution of heat around the globe, leading to changes in climate. These tectonic plates, in their relentless dance, have a profound impact on Earth's climate, influencing everything from ocean currents to atmospheric circulation patterns. The movement of tectonic plates can also affect the carbon cycle, which plays a crucial role in regulating the Earth's climate. When tectonic plates collide, they can create mountain ranges that expose new rock to the atmosphere, where it can react with carbon dioxide and remove it from the air. This process, known as chemical weathering, can help to cool the Earth's climate over long periods of time. Conversely, volcanic eruptions, which are also driven by tectonic activity, can release large amounts of carbon dioxide into the atmosphere, warming the climate. Imagine continents drifting over millions of years, changing the face of our planet. This process, known as continental drift, has been happening for as long as the Earth has existed, and it continues to this day. The continents we see today are just the latest configuration in a long history of movement and change. In the past, the continents have come together to form supercontinents, such as Pangaea, which existed around 300 million years ago. These supercontinents eventually broke apart, creating new oceans and continents in the process. The movement of continents can also create new habitats for plants and animals, driving the evolution of new species and the extinction of others. As land masses shift, they alter the flow of ocean currents, which act like giant conveyor belts, distributing heat around the globe. The movement of ocean currents is driven by a combination of factors, including the rotation of the Earth, the position of the continents, and the temperature and salinity of the water. These currents play a crucial role in regulating the Earth's climate by transporting warm water from the equator to the poles and cold water from the poles to the equator. This process helps to balance the temperature of the Earth's surface, preventing extreme heat or cold in any one region. Changes in the flow of ocean currents can have significant effects on the climate, leading to shifts in temperature and precipitation patterns. These currents play a crucial role in regulating Earth's temperature, and even a slight change in their path can have significant climatic consequences. For example, the Gulf Stream, a warm ocean current that flows from the Gulf of Mexico to the North Atlantic, helps to keep the climate of Western Europe mild and temperate. If the flow of the Gulf Stream were to change, it could lead to significant cooling in the region, with potentially serious consequences for agriculture and human populations. Similarly, changes in the flow of the Pacific Ocean currents can affect the climate of the Americas, leading to events such as El Niño and La Niña, which can cause extreme weather conditions around the world. Moreover, the collision of tectonic plates can thrust up towering mountain ranges, affecting wind patterns and precipitation levels. The formation of mountain ranges can create new climates in different regions by blocking the flow of air and creating rain shadows, where one side of the mountain range receives heavy rainfall while the other side remains dry. The uplift of the Andes, for example, has created a range of different climates in South America, from the wet Amazon rainforest to the dry Atacama Desert. The formation of mountain ranges can also create new habitats for plants and animals, driving the evolution of new species and the extinction of others. It's like rearranging the furniture on a grand scale, with each change influencing the overall climate of our planet. The movement of tectonic plates is a slow and gradual process, but over millions of years, it can have profound effects on the Earth's climate and the evolution of life. By studying the movement of tectonic plates and the changes they create, scientists can gain a better understanding of the Earth's past and make predictions about its future. The dance of continents and climate is a fascinating and complex story, one that continues to unfold with each passing day.
Welcome back, fellow explorers of the cosmos.
Today we're diving deep into the chilly depths of ice ages, those epochs when our planet dons a frosty coat.
We often hear about carbon dioxide or CO2 in the context of global warming.
And rightly so. But did you know that this potent greenhouse gas also plays a key role in the flip side of the climate coin ice ages?
You see, CO2 acts like a planetary thermostat. When concentrations are high, more heat gets trapped in the atmosphere, leading to warmer temperatures.
Conversely, when CO2 levels drop, the planet cools down. It's like adjusting the thermostat in your house, but on a cosmic scale.
Welcome back, fellow Earthlings.
In our quest to unravel the mysteries of ice ages, we've arrived at a crucial stop, the vast and mighty ocean.
Now, the ocean isn't just a giant bathtub, it's a dynamic churning system with currents that crisscross the globe, transporting heat like a giant conveyor belt.
These currents, driven by wind, salinity, and temperature differences, play a pivotal role in regulating Earth's climate.
It's like the ocean has its own circulatory system, keeping the planet's temperature in check. Greetings, fellow stargazers! Today we're exploring a fascinating phenomenon that plays a crucial role in shaping Earth's climate, the albedo effect. Now, albedo is a measure of how much light a surface reflects. Think of it like this. A mirror has a high albedo because it reflects most of the light that hits it. On the other hand, a dark surface, like asphalt, has a low albedo because it absorbs most of the light, converting it into heat.
We often think of volcanoes as destructive forces, and with good reason. The sheer power and ferocity of an erupting volcano can be both mesmerizing and terrifying. Imagine standing at a safe distance, watching as molten rock, heated to thousands of degrees, bursts forth from the Earth's crust. The ground trembles beneath your feet, and the air is thick with the smell of sulfur. It's a scene straight out of a disaster movie. But for many communities living near these geological giants, it's a very real and present danger. When a volcano erupts, it can unleash rivers of molten rock, send ash clouds soaring into the stratosphere, and trigger devastating tsunamis. These natural disasters can obliterate entire villages, reshape landscapes, and even alter the course of rivers. The immediate aftermath of an eruption is often chaos and destruction, with emergency services scrambling to save lives and contain the damage. But the story of a volcanic eruption doesn't end there. The effects can ripple outwards, impacting regions far beyond the immediate vicinity of the volcano.
But these fiery spectacles are more than just local disasters. They are a testament to the incredible forces at work beneath the Earth's surface. The magma that fuels these eruptions originates deep within the planet, in a region known as the mantle. Here, intense heat and pressure cause rocks to melt and form magma, which then rises through the Earth's crust, seeking an outlet. When it finally breaks through, the result is an awe-inspiring display of nature's power. They're powerful reminders that our planet is a dynamic, ever-changing system, and they play a surprisingly complex role in shaping Earth's climate. Volcanic eruptions can have both short-term and long-term effects on the environment. In the short term, the ash and gases released into the atmosphere can block sunlight, leading to temporary cooling. This phenomenon, known as volcanic winter, can last for months or even years, depending on the size and duration of the eruption. In the long term, the materials ejected by volcanoes can contribute to the formation of new land masses and even influence the composition of the atmosphere.
Now you might be thinking, volcanoes are hot, so wouldn't they make the planet warmer? It's a logical assumption, given the intense heat and energy released during an eruption. However, the relationship between volcanic activity and global climate is far more intricate. While the immediate vicinity of an erupting volcano certainly experiences a surge in temperature, the overall impact on the planet's climate is influenced by a variety of factors, including the type and amount of materials ejected, the altitude at which they are released, and the prevailing atmospheric conditions. And while it's true that eruptions release an immense amount of heat, their impact on global climate is far more nuanced than that. The ash and gases released into the atmosphere can have a cooling effect, as they reflect sunlight away from the Earth's surface. This cooling effect can offset the warming caused by the release of greenhouse gases, such as carbon dioxide, which are also emitted during an eruption. The net effect on global climate depends on the balance between these opposing forces.
You see, volcanic eruptions inject massive amounts of particles and gases into the atmosphere, and it's these materials that hold the key to understanding their influence on our planet's thermostat. Among the most significant of these emissions are aerosols, which are tiny particles suspended in the air. These aerosols can remain in the atmosphere for months or even years, depending on their size and composition. They can travel great distances carried by wind currents, and their effects can be felt far from the site of the eruption.
Among the most important of these volcanic emissions are aerosols, tiny particles suspended in the air. These aerosols can have a variety of effects on the atmosphere, depending on their composition and concentration. Some aerosols, such as those composed of sulfur dioxide, can reflect sunlight back into space, leading to cooling. Others, such as those composed of black carbon, can absorb sunlight and contribute to warming. The overall impact of aerosols on the climate depends on the balance between these opposing effects. These aerosols, composed of things like sulfur dioxide, have a remarkable cooling effect on the planet. When sulfur dioxide is released into the atmosphere, it reacts with water vapor to form tiny droplets of sulfuric acid. These droplets act like tiny mirrors, reflecting sunlight back into space and preventing some of the sun's energy from reaching the Earth's surface. This cooling effect can be significant, especially following a major eruption. For example, the eruption of Mount Pinatubo in 1991 led to a global temperature decrease of about 0.5 degrees Celsius for several years.
They act like tiny mirrors, reflecting sunlight back into space and preventing some of the sun's energy from reaching the Earth's surface. This phenomenon, known as global dimming, can have a variety of effects on the climate. In addition to cooling the planet, it can also influence weather patterns, precipitation, and even the growth of plants. The impact of volcanic aerosols on the climate is a complex and ongoing area of research, with scientists working to better understand the mechanisms involved and their implications for the future. Scientists around the world are dedicated to studying volcanic activity and its effects on the environment. By analyzing the materials ejected during eruptions, they can gain insights into the processes occurring deep within the Earth. This research not only helps us understand the immediate impacts of volcanic eruptions, but also provides valuable information about the long-term evolution of our planet. For example, the study of ancient volcanic rocks can reveal clues about past climate conditions and the history of Earth's atmosphere. Volcanic eruptions are a reminder of the incredible power and beauty of our planet. They are a testament to the dynamic nature of the Earth and the forces that shape its surface. While they can be destructive and dangerous, they also play a vital role in the ongoing evolution of our planet. By studying these natural phenomena, we can gain a deeper appreciation for the complexity and interconnectedness of the Earth's systems. The landscapes created by volcanic activity are some of the most stunning and unique on Earth. From the rugged peaks of volcanic mountains to the lush, fertile soils of volcanic islands, These environments are rich in biodiversity and natural beauty. Volcanic soils are often highly fertile, supporting a wide variety of plant and animal life. In many parts of the world, communities have learned to live in harmony with these powerful forces, harnessing the benefits of volcanic activity while mitigating the risks. Volcanic activity also provides a source of geothermal energy, which can be harnessed for a variety of purposes. Geothermal power plants use the heat from the Earth's interior to generate electricity, providing a clean and renewable source of energy. In addition, geothermal hot springs and geysers are popular tourist attractions, drawing visitors from around the world to experience the natural wonders of volcanic landscapes. Advances in technology have allowed us to monitor volcanic activity with greater precision than ever before. Satellites equipped with sensors can detect changes in the Earth's surface, gas emissions and thermal activity, providing early warning of potential eruptions. This information is crucial for disaster preparedness and response, helping to save lives and minimize the impact of volcanic events. By combining satellite data with ground-based observations, scientists can build a comprehensive picture of volcanic activity and its effects on the environment. The study of volcanoes is a fascinating and ever-evolving field, with new discoveries being made all the time. From understanding the mechanisms that drive eruptions to exploring the impacts on climate and ecosystems, there is always more to learn. As we continue to study these powerful natural phenomena, we gain a deeper appreciation for the complexity and beauty of our planet. Volcanic eruptions are a reminder of the dynamic forces at work beneath our feet and the ever-changing nature of the Earth. In conclusion, volcanic eruptions are a powerful and awe-inspiring reminder of the dynamic nature of our planet. They are both destructive and creative forces, capable of reshaping landscapes and influencing global climate. By studying these natural events, we can gain valuable insights into the processes that shape our world and better prepare for the challenges they present. Whether viewed from a safe distance or experienced up close, the spectacle of a volcanic eruption is a testament to the incredible power and beauty of the Earth.
The sun, that giant glowing ball of plasma that keeps our planet bathed in light and warmth. It's the ultimate source of energy for life on Earth, driving everything from photosynthesis to weather patterns.
But the sun isn't just a static source of light and heat. It's a dynamic, ever-changing star, and its activity can have a surprising impact on our planet's climate.
One of the most visible signs of the sun's activity is the appearance of sunspots, those dark, cooler regions that dot the solar surface. Now, these sunspots might seem like small blemishes on the face of the sun, but don't let their appearance fool you.
They're powerful indicators of intense magnetic activity, and their fluctuations can have subtle but measurable effects on Earth's climate. Have you ever noticed how a black car gets much hotter in the sun than a white one? That's because darker surfaces absorb more sunlight, while lighter surfaces reflect more of it away. This simple principle, known as albedo, plays a crucial role in shaping Earth's climate, particularly when it comes to ice ages. Albedo is a measure of how much solar radiation a surface reflects back into space. It's expressed as a percentage, with 0% representing complete absorption and 100% representing perfect reflection. Now, ice and snow, with their bright white surfaces, have a very high albedo, reflecting a significant portion of sunlight back into space.
You know, we often think of the ocean and the atmosphere as separate entities, right? We see the ocean as this vast, mysterious expanse of water, teeming with life and secrets, while the atmosphere is this invisible blanket of air that we breathe, filled with clouds and weather patterns. But what if I told you that these two seemingly distinct realms are actually deeply intertwined, constantly interacting in ways that shape our world in profound ways?
But in the grand cosmic ballet of Earth's climate system, they're more like dance partners locked in a perpetual intricate waltz. Imagine the Earth as a grand ballroom, where the ocean and the atmosphere are the star dancers moving in perfect harmony. Their dance is not just a simple back and forth, it's a complex, dynamic interaction that involves the exchange of energy, moisture, and gases. This dance is what drives the weather patterns we experience every day, from gentle breezes to powerful storms and even the long-term climate trends that shape our planet over millennia. The ocean, this vast, churning body of water, and the atmosphere, this thin, delicate veil of gas, are constantly exchanging energy and matter. Picture the ocean as a giant cauldron, constantly stirred by the winds and heated by the sun. The surface of the ocean absorbs sunlight, warming the water and causing it to evaporate. This water vapor rises into the atmosphere where it cools and condenses to form clouds. These clouds can travel great distances carried by the winds and eventually release their moisture as precipitation, feeding rivers and lakes and replenishing the ocean. This cycle of evaporation and precipitation is a key part of the water cycle, which is essential for life on Earth. This exchange, my friends, this constant interplay, is what drives our planet's weather patterns, and you guessed it, plays a pivotal role in the ebb and flow of ice ages. The ocean and atmosphere work together to distribute heat around the globe, creating the conditions for different climates and weather patterns. For example, the warm waters of the Gulf Stream help to keep Europe relatively mild, while the cold waters of the Humboldt Current bring cool, nutrient-rich waters to the coast of South America, supporting a rich diversity of marine life. Over longer timescales, changes in the ocean and atmosphere can trigger ice ages and periods of warming, shaping the history of our planet.
Now let's delve a little deeper, shall we? The ocean is not just a passive recipient of energy from the sun and the atmosphere. It plays an active role in regulating the Earth's climate. One of the key ways it does this is through its enormous heat capacity. The ocean can absorb and store vast amounts of heat, much more than the atmosphere or the land. This means that the ocean can act as a giant heat sink, absorbing heat during periods of warming and releasing it during periods of cooling. This helps to moderate global temperatures, preventing extreme fluctuations and creating a more stable climate. The ocean, with its enormous heat capacity, acts like a massive heat sink, absorbing and releasing solar energy, influencing atmospheric temperatures over vast stretches of the globe. This process is not uniform. Different parts of the ocean absorb and release heat at different rates, creating a complex pattern of temperature variations. For example, the warm waters of the tropics absorb a lot of heat, while the cold waters of the polar regions release heat. This creates a temperature gradient that drives ocean currents, which transport heat around the globe. These currents play a crucial role in regulating the Earth's climate, influencing everything from the weather patterns we experience on a daily basis to the long-term climate trends that shape our planet.
Meanwhile, the atmosphere, with its winds and storms, drives ocean currents, transporting heat from the tropics towards the poles, moderating global temperatures and shaping the very landscapes that we call home. The interaction between the ocean and the atmosphere is a two-way street. The winds and storms in the atmosphere can drive ocean currents, pushing warm water from the tropics towards the poles and bringing cold water from the poles towards the equator. This helps to distribute heat around the globe, creating a more balanced climate. At the same time, the ocean can influence the atmosphere with the heat and moisture it releases, affecting weather patterns and climate. This dynamic interplay between the ocean and the atmosphere is a key part of the Earth's climate system, and understanding it is essential for predicting and responding to changes in our climate. We often think of life as a passive passenger on this pale blue dot we call Earth. But the truth is, life isn't just along for the ride. It's an active participant, a sculptor of worlds, even influencing the very climate that surrounds it. From the oxygen we breathe to the carbon dioxide that helps regulate our temperature, life, my friends, has been shaping Earth's climate for billions of years. From the grand cycles of Earth's orbit to the subtle dance of ocean currents, we embark on a journey that spans millennia. These cycles, often imperceptible in our daily lives, are the silent architects of our planet's climate. The tilt and wobble of Earth's axis, the shape of its orbit around the Sun, and the distribution of solar energy across the globe all play crucial roles in the ebb and flow of ice ages. These celestial mechanics, though seemingly distant, have profound impacts on the climate systems that sustain life on Earth. From the powerful influence of volcanic eruptions to the intricate workings of the carbon cycle, we see how Earth's internal processes contribute to its climatic narrative. Volcanic eruptions, with their dramatic displays of fire and ash, release vast quantities of particles and gases into the atmosphere. These particles can reflect sunlight, leading to temporary cooling periods. Meanwhile, the carbon cycle, a complex web of interactions between the atmosphere, oceans, and living organisms, regulates the levels of carbon dioxide, a key greenhouse gas. This delicate balance between carbon sources and sinks is vital for maintaining the planet's temperature. The story of ice ages is a testament to the interconnectedness of our planet's systems. It's a story of change, of cycles within cycles, of forces both immense and infinitesimal shaping the world we know. Glaciers, those colossal rivers of ice, advance and retreat in response to climatic shifts, carving out landscapes and influencing sea levels. Ocean currents, driven by temperature and salinity differences, act as global conveyors of heat, redistributing energy around the planet. Tectonic plates, the massive slabs of Earth's crust, shift and collide, creating mountains and ocean basins that alter atmospheric and oceanic circulation patterns. These dynamic processes, working in concert, have sculpted the Earth's surface and climate over millions of years. As we've journeyed through the science behind these periods of global chill, we've delved into the methods scientists use to unravel the mysteries of past climates. Ice cores drilled from the depths of glaciers and ice sheets serve as time capsules, preserving records of atmospheric composition, temperature, and volcanic activity. By analyzing the layers of ice, scientists can reconstruct climate conditions stretching back hundreds of thousands of years. This invaluable data provides insights into the natural variability of Earth's climate and the factors that have driven past ice ages. I hope you've gained a deeper appreciation for the complexity and fragility of Earth's climate. The intricate interplay of natural forces that govern our climate is a delicate balance, one that can be easily disrupted. As we witness the seasonal transitions in nature, from the budding of spring to the dormancy of winter, we are reminded of the cyclical nature of life on Earth. These cycles, while predictable, are also vulnerable to external influences, both natural and anthropogenic. The forces that tipped our planet into ice ages past are still at play today, albeit in different forms and magnitudes. The same orbital variations, volcanic activity, and carbon cycle dynamics continue to influence our climate. However, the rapid pace of modern climate change, driven by human activities, adds a new layer of complexity to this ancient story. The retreat of glaciers, the warming of oceans, and the shifting of weather patterns are all indicators of a changing climate, one that is increasingly influenced by human actions. Intertwined with the growing influence of human activity, the natural forces that have shaped our climate for eons are now being altered by industrialization, deforestation, and the burning of fossil fuels. These activities release vast amounts of greenhouse gases into the atmosphere, enhancing the natural greenhouse effect and leading to global warming. The consequences of this warming are far-reaching, affecting ecosystems, weather patterns, and sea levels. The delicate balance that has maintained Earth's climate for millennia is now being disrupted, with potentially catastrophic consequences for life on our planet. Understanding these forces, both natural and human-induced, is not just an academic pursuit. It's essential for navigating the challenges of a changing climate and ensuring a sustainable future for generations to come. Scientists around the world are working tirelessly to study climate data, model future scenarios, and develop strategies for mitigation and adaptation. By analysing trends and patterns, they aim to predict the impacts of climate change and inform policy decisions. The knowledge gained from this research is crucial for building resilience and reducing vulnerability to climate-related disasters. Embracing renewable energy sources such as wind, solar and hydroelectric power is a key step towards reducing our carbon footprint and mitigating climate change. Community-led sustainability projects, from reforestation efforts to sustainable agriculture practices, demonstrate the power of collective action in addressing environmental challenges. Urban planning for climate resilience, including the development of green infrastructure and the promotion of energy-efficient buildings, is essential for creating sustainable cities that can withstand the impacts of a changing climate. These initiatives, driven by innovation and collaboration, offer hope for a more sustainable and resilient future. Thank you for joining us on this journey through the science behind ice ages. We've explored the intricate web of natural forces that have shaped our planet's climate, from the grand cycles of Earth's orbit to the subtle dance of ocean currents. We've delved into the powerful influence of volcanic eruptions and the intricate workings of the carbon cycle. We've witnessed the interconnectedness of our planet's systems and the delicate balance that sustains life on Earth. Through the lens of science, we've gained a deeper understanding of the complexity and fragility of our climate. We hope you found this exploration as enlightening as we did. The journey through the science of ice ages has been a testament to the power of curiosity and the pursuit of knowledge. Behind the scenes, a dedicated team of researchers, scientists, and filmmakers have worked tirelessly to bring this story to life. Their passion and commitment to understanding our planet's climate are truly inspiring. As we celebrate the culmination of this project, we are reminded of the importance of science communication in bridging the gap between research and public awareness. Don't forget to like, subscribe, and share for more in-depth scientific content. By staying informed and engaged, you can be part of the solution to the challenges posed by climate change. Together, we can make a difference and ensure a sustainable future for generations to come. Thank you for watching, and we look forward to bringing you more fascinating explorations of the natural world.